Everybody, welcome with me, Bonnie Webster from UK, where it's in the Natural History Museum, and you will be surprised that they are doing a lot of also research, and this is always very important. Bonnie is a great scientist. She did a lot of work for schistosomiasis in Africa, and she has implemented also rapid extraction on these applications in African setting to help people identify diseases more efficient and very fast. And I'm so happy that she agreed to be with us today and give very nice presentation, I'm sure, about her adventure in Africa and to extract schistosomiasis. So, Bonnie, the mic is yours.
Thank you very much, Ahmed. And it's lovely to be here today and to have such a great audience as well. So as Ahmed introduced me, so yeah, very much I work in very low resource settings, and this picture on the slide really shows those settings and a typical transmission site for schistosomiasis. So just before I start, I really want to just acknowledge various people involved in a lot of the work that I'm going to present today, particularly an array of students who have really pushed this work forward through very small amounts of money, but it's really showed how quickly we can progress with some of these methods as well. Just also like to acknowledge particularly field colleagues and access to samples as well. So first I'm just going to give a very brief background to schistosomiasis, mainly for those who don't know about the disease, because this is very important to think about which sample types we're using, as this really affects the extraction methods and also the analysis that we do. So it's termed a neglected tropical disease, so it's a disease of poverty and of neglected people. And worms live in blood vessels around the intestines or the urinary tract, and through that, eggs are then released in urine or stool samples. And it's these samples that we really focus on in terms of molecular diagnostics, but we can also look at blood samples as well, where we look for cell-free or circulating DNA. So there's two types of the disease. So medical schistosomiasis is split into intestinal schistosomiasis, which is the main form, and then urogenital schistosomiasis, and this is caused by one species. So this is what we're focusing on today. And as Ahmed talked about as well, we've really focused on this because it's a lot more easier than looking at intestinal schistosomiasis and looking at stool samples. And also we're very interested with a morbidity characteristics of these infections known as genital schistosomiasis, particularly female genital schistosomiasis, where women are highly stigmatized through having chronic infections that lead to infertility. And it's also highly associated with things like STIs and HIV. So schistosomiasis is, urogenital schistosomiasis here is widespread throughout Sub-Saharan Africa, and also pockets in the Arabian Peninsula. But we also have outbreaks coming into the Mediterranean region. So there was also a recent outbreak in Corsica, and transmission is ongoing in Corsica. So for many of the NTDs, because they're very much neglected and these infections are very chronic, there is severe diagnostic gaps for many of the diseases. And the reassured criteria is put on the diagnostic needs for many of these NTDs. And this is to make them very simple and user-friendly, and to be able to deliver them at the point of need. But it's very difficult to achieve some of these goals, and there's always a very fine balancing act between cost and simplicity and accuracy of our diagnostics. And for a disease such as schistosomiasis, which we term mass drug administration disease, where we do mass drug administration to control, we don't routinely diagnose people and then treat them. We just routinely do mass drug administration in high-risk populations, particularly children. We can see our diagnostic need does change as we move through control. At very high levels of disease, we can use things like microscopy, which are very cheap and rapid. But as we move down to elimination or transmission interruption, our diagnostics need to become much more sensitive, specific, and we need to start to be able to implement them at the point of need. And again, we still need to think about that fine balancing act between cost, simplicity, and accuracy. So the WHO has now tasked the schistosomiasis researchers and NGOs to actually eliminate schistosomiasis by 2030 in all 78 endemic countries. And we have diagnostics as this, but there's major modifications needed to make them applicable and make them reach those targets. And recently, the target product profile for diagnostics for schistosomiasis was published, really putting the characteristics on the diagnostics needs to reach elimination. And some of the main characteristics, there's again very tall asks within this TPP, such as zero infrastructure. The diagnostic need to be very simple and portable, and they need to be in low numbers of steps required by the diagnostic user. So for the molecular diagnostics, we're really focusing on this mid-stage of disease control. We have some developments in antigen tests, but we also need to look at molecular tests offering that really high sensitivity and specificity. And we need these tests to allow us to make decisions about moving from mass drug administration to targeted treatment, and then making decisions about stopping treatment. We also know we have mass drug administration fatigue, where people are asking for a diagnosis before they're treated. We also have hidden morbidities, which we need to diagnose, such as genital lesions, and also very low levels of infection. And we also need good diagnostics for long-term monitoring. Because this disease is transmitted through snails, which really amplify the transmission larval stage, resurgence is going to be a real problem looking down the line towards elimination and also eradication. So just focusing on the molecular techniques here. So we know PCR is the standard method, but we also really have a lot of focus now on these isothermal methods because they're highly portable and field friendly, just like Ahmed has been talking about in his previous talk. But developing diagnostics, the main focus often at the early stage of development is always the amplification and detection steps. But it's really just to point out that the sample prep and what sample you're using is a major step to actually being able to implement the latter stage of the amplification and detection in the field. And there's many things we need to think about. We need to think about things like how do we collect the sample, what quality of sample we need, how stable it is, particularly in those endemic settings. How do we store those samples? How stable they are when we actually amplify the DNA, and also the inhibitors that are present in those samples. And for field-based diagnostics, we need protocols which are very simple. We need low resources and equipment, and we also need the reagents and the equipment to be very stable, particularly in those hot, humid environments. So we're not focusing on the amplification or detection step, but I just want to point out here that a lot of the work that I'm going to present in the next slides is very much focused on recombinase polymerization amplification assays, which is very simple, accurate, fast, and portable. Obviously, most people know about LAMP, but again, RPA is also a very, very good and accurate isothermal method. So just a quick overview of our workflow for RPA so you can kind of understand the output from our data. So we take samples, and today I'm going to present work on both urine, but I'm also going to talk about some of the work we've been doing on lavages from cervical vaginal samples, looking at FGS, and also self-swab samples as well. So this is what we'll be focusing on, that extraction method here, both pure and crude. And then we set up our RPA assay and we analyze our samples within a fluorometer, which gives us nice outputs of fluorescence increase for positive samples. The eggs come through in the urine samples for infected individuals. There's a nice video here of one of those eggs hatching, just to show you the type of material that we actually get with our urine. So the eggs actually hatch through osmosis, and water goes into the egg and makes it burst, and then releases this larval stage. But we also don't know if we get cell-free parasite DNA within our samples as well. So we've got the opportunity to look at both those types of DNA, but again, working out which one we're actually targeting and analysing is quite difficult. These urine samples come in various stages of pathology, or there's other things within these samples. For instance, this just shows you we can have samples which are very high in urea. If people are very dehydrated, they have other things in them like bacteria. We can also get large quantities of blood, not just from schistosomiasis, but also other infections as well. And for female genital schistosomiasis, so the main form of diagnosis is looking into the vaginal passage and looking for lesions. And this is very invasive, and it's not often welcomed by the patients as well. So we've been doing a lot of work on collecting samples, and particularly self-swab samples from women, to empower them to actually provide samples independently and to allow them to get a diagnosis rapidly. So just an overview of the procedures that we've been using. So we've been very much focused on using what we call the SpeedXtract Kit, or now the Swift DNA Kit. And it's really proved to us a very useful and very important method within our workflows for our diagnosis in the field. So just a quick overview of the procedure. We do cell binding using the EN buffer. This allows us to capture the cells on a magnetic rack. And then we do liquid dispose of the liquid with the cells captured on the beads. And just here, I'd just like to point out that we can, for schistosomiasis, we really need to upscale the throughput for our analysis. So we're spending a lot of time now looking at more high throughput systems for magnetic extraction. For instance, this is a device that has 96 magnetic rods that you can use for extractions. With COVID, there's huge advancements now within the technology to doing multiple extractions on scale. So then we do the cell lysis step, releases the DNA. We're doing the heating step, and then we're doing the DNA elution and collecting our DNA. So that's the standard protocol that we were going forward with. So just as I said, we're pointing out about actually making this more high throughput. And also we were trying to reduce our steps within our protocols. And that's some of the work that we've been doing very much more recently, and I'll present at the end of this presentation. But also we've been thinking about how we also reduce the equipment needs, particularly for schistosomiasis. And we do find that this heating step can be sometimes problematic if we really don't have electricity and also the time needed to actually heat these samples to the appropriate temperature. So using the SpeedXtract, we did some very nice spiking experiments in our lab where we were extracting DNA from single eggs up to 100 eggs. And again, you can see here that with the RP analysis, our limited detection of a single egg within a spiked urine sample was very, very effective. And the method was very, very robust, quick, and simple. We were then able to move out into the field to actually test some real samples, some clinical samples. And we're very fortunate to work with a group in Zanzibar, which is, and Zanzibar is set for elimination of schistosomiasis through multiple decades of control on Zanzibar. So we're down to very low levels of infection with very low levels of intensity of infections within our samples. We have access to large numbers of frozen urine samples from these control programs, which is a fantastic resource for testing our diagnostics. So within the study, we're able to look at 200 urine samples with varying egg counts from 0 to 500 eggs per 10 ml. We took a very random sample, and we really did not have the resource to actually perfect our protocol at this point. So we just took a very random sample of 50 microliters of these urine samples, and then followed our standard Swift DNA extraction method. And we got very nice data. So this is comparing our samples to microscopy. And you can see here, we're really focused on these very low egg counts within our samples, looking at our limits of detection. And you can see we've got 91 to 92% positivity within our samples. So that gave us very nice data. But we did question about these samples being frozen. Is that allowing the eggs to be broken up more easily and the DNA to be released? And so was this method actually able to release from actual viable eggs? But very nicely, Michael, who's talking today as well, has used this method in Ghana, looking at urogenital schistosomiasis, looking at urine sediments. And again, he got very good, nice results using clinical samples that had not been frozen, with high sensitivity and specificity rates as well, which proved that this method was very effective in the field. And he had also cut out these first stages of the cell binding and the magnetic attraction of those cells as well, showing that we could simplify our methods as well. And then moving on to female genital schistosomiasis samples. So here we really do want to focus on self-swab samples. And this has really proved through qPCR, this is a very effective form of diagnosis. So we wanted to test our field extraction methods and also our RPA methods on diagnosis. We were very lucky to be involved in this very large study where we were able to compare and contrast different methods of extraction, so DNA Easy by QIAGEN, a very quick lysis step, and also the SpeedXtract kit, and we were able to compare RPA and PCR as well. So the data I'll show you now is just using these lavage samples, about 223 samples, and we were following our standard procedure again, really, as we had no way of doing some preclinical testing for the extraction optimization here as well. But you can see from this, we had good sensitivity and specificity rates using these methods. The vaginal cell swab samples we could only test these samples using a pure extract kit, but again it just showed that this would have very good data if we were able to use these more crude methods. So this pilot data is very promising. We think we can make improvements and modify the steps involved to make it more quick and simple. We still don't know what type of DNA we're extracting these samples. Is it egg DNA, cell DNA, or cell-free DNA? But we also think we can come up with protocols or test protocols that is direct lysis, putting a swab straight into the cell lysis buffer and DNA release, and then eluting that with a magnetic rack extraction method. So this has great promise for the future as well. And just to finish off, 2 slides on some recent further laboratory tests we've been doing. And it's also very important to point out that this is very specific to schistosomiasis, and it won't work for all diseases or all methods of analysis. So we've been taking, and just to point out, these are frozen eggs again. We've been putting eggs directly into our RPA. We've also been adding crude urine to see what tolerance we have within our assays. And we know now that we can put direct eggs straight into RPA assays and we get amplification. We also know that we can add crude urine and that does not affect our RPA amplification. And we can really max out the reaction with the amount of urine, replacing all the water in the reaction, which shows that it's very tolerant to urine within that analysis. But again, this really does need to be validated on clinical samples to really test what real life eggs will do, and also to look at the diversity of those kind of urines that we face. So we've also been trying to reduce the steps for the Swift DNA protocol, again using frozen eggs with and without urine, removing this first step of cell concentration, and also removing the heating step. And very nicely, it worked as well. So we can do this with single eggs. We can remove the heating step, and we can remove this first stage of cell concentration. And just to point out, 2 very good students in my lab, Dr. Owen and Sylvia, who've been working through these protocols and testing various forms. So this shows that we can really simplify the method to actually reduce it down to a few steps. But again, we need to validate this on clinical samples. And as I mentioned earlier, we'd really like to focus on those FGS samples, even direct extraction, also those that are preserved in things like the transport media, which is now used very much for COVID samples. And last slide, just to really show you that we've been doing some very, lots of comparisons of different methods. And this is the RPA data from single eggs from things like lysis buffers at different temperatures, QIAGEN kits, which again don't give us quite such good data. Other commercial kits which are said to be very field applicable, but actually didn't tend to work very well, and also those direct eggs. So it's important to acknowledge that even though methods might be described as being very field applicable, they might not use for your disease or your assay. So the final questions that we face now is that we really want to increase our throughput for our sample preparation analysis so we can do mass screening and also implement test and treat scenarios in our endemic settings. For urine, we need to figure out if we need to concentrate our samples to actually get those eggs into a more concentrated format and increase sensitivity, or even look at cell-free DNA within our samples. And as I said there, we need to think about how we analyse different forms of the DNA, and particularly cell-free DNA. We need to look at the stability of our samples in the field and how things like just transporting them from field sites or being sitting in hot temperatures might affect them, and also look at diversity of samples. And we also want to focus on things like blood and also stool samples, as those are going to be very important for other forms of the disease as well. So I'll finish there, and just a very big thank you to Andy Wend at Xpedite. He's a fantastic person who responds very quickly to all inquiries and will actually support you in optimizing your methods. And of course, Dr. Ahmed, who's absolutely brilliant and a brilliant collaborator in actually supporting all of the work that we've been doing. And that's the end. Thank you very much.